All right, so have you seen Tenet?
I have, yeah.
That whole time thing
Yeah.
with the bullets and the reverse entropy and all that?
Oh, yeah.
Kind of wild concept. I mean, it plays fast and loose with the physics.
Oh, for sure.
But that idea that disorder could decrease,
Yeah.
that time could flow backwards. I mean,
Mhm.
that's entropy at its most mind-bending.
Yeah.
But entropy is more than just a sci-fi plot device.
Yeah.
It's like woven into the fabric of the universe.
Yeah.
It's working its magic all around us.
Right.
Even something as simple as like an ice cube melting
Yeah.
or a sandcastle crumbling on the beach, that's entropy in action.
Yeah, what's fascinating is that while those examples are really easy to visualize, I mean, entropy governs everything from the behavior of black holes to the fate of the universe itself.
Exactly.
And it's not just a concept confined to physics, right? I
Yeah.
mean, it pops up in technology, fuels artistic expression. It even shapes our understanding of time.
And that's exactly what we're going to be diving into today, exploring entropy from its scientific roots to its cultural impact. Unpacking everything from the second law of thermodynamics to how entropy influences data compression and even the security of cryptocurrencies like Bitcoin.
Right, like Bitcoin.
Yeah.
Now, before we get lost in the weeds, I'm kind of curious. What comes to mind when you hear the word entropy? Is it something you've encountered before, maybe in school or just out in the wild?
I think for a lot of people, entropy is kind of this shrouded term. It's often associated with disorder, chaos.
Right.
But at its core, it's really just a measure of the randomness or the number of possible arrangements within a system.
Okay.
So the more ways you can arrange the pieces of a system, the higher the entropy.
Oh, okay, I see.
So it's like having a deck of cards. There's only one way to have them perfectly ordered.
Right.
But shuffle them and the possibilities just explode,
Yeah.
increasing the entropy.
So a messy desk with paper scattered everywhere would have higher entropy than a perfectly organized one where everything is in its place.
It's kind of relief to know that there's a scientific explanation for my chronic disorganization.
Precisely. And to illustrate this further, let's revisit those examples you mentioned earlier.
Okay.
So when an ice cube melts, the water molecules transition from a very neatly ordered crystalline structure to a much more chaotic, freely moving arrangement in that liquid form.
Right.
Similarly, when water boils and turns into steam,
Yeah.
the molecules spread out even further, increasing their randomness and thus entropy.
So those visual examples are really great ways to kind of illustrate this concept of increase in entropy.
Yeah.
But who were the pioneers? Who were the ones who cracked the code on this fundamental force of nature?
Yeah, so the foundations of our understanding of entropy, we can really trace them back to two brilliant minds,
Okay.
Rudolf Clausius and Ludwig Boltzmann.
Okay.
Clausius, he was working in the mid-1800s and actually coined the term entropy
Oh, wow.
and formulated the second law of thermodynamics.
That's quite a legacy.
Yeah.
So what exactly did Clausius bring to the table?
So his second law of thermodynamics is really a game changer.
Okay.
It essentially states that in an isolated system, and think of the entire universe, entropy will always increase over time, or at best, remain constant. It never decreases.
Right.
So this explains why heat always flows from hot objects to colder ones.
Right.
Why coffee gets cold and never spontaneously heats up. There's no undo button for entropy.
So no rewind in time, no escaping the inevitable increase in disorder. That explains a lot about life. What about Boltzmann? How did he contribute to our understanding?
So Boltzmann took Clausius's work and kind of gave it a statistical twist, connecting entropy to the microscopic behavior of atoms and molecules.
Okay.
You see, Clausius focused on the macroscopic observable aspects of entropy.
Right.
But Boltzmann delved deeper, showing that entropy is directly related to the probability of a system's state. He even developed a very famous equation that quantifies this relationship, linking entropy to the number of possible microscopic arrangements,
Right.
for a given macroscopic state. It's a landmark achievement, and it's even engraved on his tombstone.
Now that's dedication.
Yeah.
Seems like these guys were truly passionate about cracking the entropy code.
They absolutely were, and their work laid the groundwork for some incredible discoveries in cosmology and theoretical physics, which we'll dive into next. But before we do that, let's touch on a crucial point about Boltzmann's work.
Okay.
His equation, it elegantly demonstrates how entropy is fundamentally connected to information. Remember how we talked about the deck of cards?
Yeah.
Well, a perfectly ordered deck has very little information content. You know exactly what card is where.
Right.
But a shuffled deck, It's packed with information because there are so many possible arrangements.
That's a great connection to something we're all familiar with, data compression.
Oh, yeah.
Think about compressing a file on your computer.
Yeah.
A more ordered file with repetitive patterns has lower entropy, and it can be compressed more efficiently.
Absolutely.
A random disordered file, not so much.
Exactly. That's a fantastic way to think about it. Entropy plays a crucial role in information theory and computer science, which we'll explore later in our deep dive. But for now, let's shift our focus to the big leagues. The pioneers who built upon Clausius and Boltzmann's foundation to unravel the cosmic implications of entropy.
All right, let's do it.
So we've got these giants, Clausius and Boltzmann, laying the groundwork for understanding entropy.
Right.
But the story doesn't end there.
Okay.
Think about black holes. Those enigmatic cosmic objects that devour everything in their path?
Yeah. Okay, black holes, the cosmic vacuum cleaners. How does entropy fit into that picture?
Right.
They seem to defy everything we've talked about so far.
Right. You would think that, wouldn't you? But Hawking kind of turned our understanding of black holes upside down.
Okay.
He showed that black holes actually possess entropy, a lot of it, in fact. Yeah. It's proportional to the surface area of their event horizon.
Okay.
That boundary beyond which nothing, not even light, can escape.
So even the most powerful objects in the universe can't escape the grip of entropy.
Nope.
But if nothing can escape a black hole, how can it have entropy, which is all about the number of possible states?
That's the brilliant part.
Okay.
Hawking showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon.
What?
It's called Hawking radiation, and it's mind-blowing.
Okay.
Imagine particle-antiparticle pairs popping into existence near the event horizon. One particle falls in, and the other escapes, carrying away energy and information. This process causes the black hole to slowly evaporate, losing mass, and eventually disappear completely.
So information isn't truly lost in a black hole. It slowly leaks out through Hawking radiation.
That's right.
That's incredible.
Yeah.
But I'm still trying to wrap my head around it.
It's definitely one of those concepts that stretches our understanding of the universe, and Hawking's work on black hole entropy, connected general relativity, quantum mechanics, and thermodynamics in a way that was truly revolutionary.
Wow.
But speaking of the universe, there's another giant in the field of entropy we need to talk about, Roger Penrose.
Oh, okay. Roger Penrose, the guy who just won the Nobel Prize for his work on black holes.
Yes.
Wasn't he also instrumental in proving the Big Bang actually happened? How does his work connect to entropy?
Penrose has made profound contributions to our understanding of entropy's role in cosmology, particularly in the context of the Big Bang.
Okay.
He argued that the universe started in a state of incredibly low entropy, which is mind-boggling when you think about all the chaos and disorder we see today.
Yeah, that seems counterintuitive. How could the Big Bang, this massive explosion of energy and matter, have low entropy? Wouldn't it have been the ultimate state of chaos?
That's a great question, and it gets to the heart of why Penrose's work is so important. See, the early universe was incredibly uniform and smooth, even though it was incredibly dense and hot. It's like having all the air molecules in a room perfectly evenly distributed.
Okay.
That's a very ordered, low entropy state, and it's this initial low entropy that allowed for the formation of stars, galaxies, planets, and eventually life.
So in a sense, we owe our existence to the low entropy conditions of the early universe.
Exactly.
That's a pretty profound thought. But if entropy always increases, shouldn't the universe eventually reach a state of maximum entropy where everything is evenly distributed and nothing interesting can happen anymore?
You're talking about the heat death of the universe,
Yeah.
a concept that has fascinated and terrified physicists for centuries. It's the idea that as entropy increases, the universe will eventually reach a state of thermodynamic equilibrium where energy is uniformly spread out and no more work can be done. Stars will burn out, black holes will evaporate, and the universe will become a cold, dark, and lifeless void.
Wow, that's a pretty bleak picture. Is there any way to avoid this cosmic fate?
Well, there are other theories out there that challenge the idea of a simple heat death.
Okay.
Penrose, for example, has proposed the conformal cyclic cosmology model.
Yeah.
This model suggests that the universe goes through cycles of expansion and contraction, with the end of one cycle giving rise to the beginning of the next.
Okay.
He argues that the extremely low entropy state of the Big Bang is a result of a kind of cosmic reset button that gets hit at the end of each cycle.
So it's like a cosmic heartbeat, a never-ending cycle of expansion, contraction, and rebirth.
In a way.
And with each new cycle, entropy gets a chance to start fresh.
Yeah.
But wouldn't that wipe out everything that existed before?
That's one of the big questions that Penrose's model tries to address. It's a mind-bending concept, and it challenges our linear view of time. But it also opens up some fascinating possibilities. What if information from previous cycles somehow survives the transition? Could there be echoes of past universes imprinted on the fabric of our own?
Okay, now we're really venturing into the realm of science fiction.
Yeah.
But I love how exploring entropy leads us down these rabbit holes of cosmological mysteries.
It's true. Entropy is like a key that unlocks some of the deepest questions about the nature of reality.
Yeah.
And it's not just Penrose and Hawking who are pushing the boundaries of our understanding. There are other brilliant minds like Sean Carroll, Lisa Randall, and Carlo Rovelli who are exploring the profound implications of entropy on everything, from the arrow of time to the very structure of the universe.
It sounds like entropy research is thriving. What are some of the key questions these contemporary thinkers are grappling with?
Well, one of the most fascinating areas of exploration is this connection between entropy and the arrow of time.
Okay.
You know, why does time seem to flow only in one direction from past to future?
Right. Like, why can't we unscramble an egg?
Exactly, or unspill coffee.
Yeah.
Sean Carroll, for example, argues that the answer lies in the low entropy state of the early universe. He suggests that this initial condition kind of set the direction of time's arrow, driving the universe towards ever-increasing entropy.
So you're saying that the reason we experience time moving forward is because the universe is constantly moving towards a state of greater disorder.
That's the basic idea.
That's a pretty profound thought, but it also makes me wonder, could we ever manipulate entropy to control time? I mean, that's the premise of Tenet, right?
It's a question that sci-fi has been exploring for decades, and while Tenet takes some creative liberties,
Right.
it does tap into a very real question. What if we could reverse entropy locally?
Okay.
What would the consequences be?
Yeah.
Would it allow us to travel back in time or alter the course of events?
Okay, that's getting into some serious mind-bending territory.
Yeah.
What about Lisa Randall and Carlo Rovelli? What are their contributions to the entropy conversation?
So Lisa Randall, she dives into this mind-boggling world of particle physics and cosmology, exploring how entropy might behave differently in extra dimensions. You see, string theory and other models of the universe suggest there might be more spatial dimensions than the three we experience. Randall's work explores how these extra dimensions could influence the distribution of energy and information, potentially altering our understanding of entropy's role in the universe.
Extra dimensions. So we're talking about realms beyond our perception.
Exactly.
That could have their own unique entropy dynamics.
That's right.
That's some next level stuff.
Yeah.
And what about Rovelli?
So Carlo Rovelli, he's a fascinating thinker who kind of blends physics and philosophy in a way that's both illuminating and thought-provoking.
Yeah.
He argues that our experience of time is actually an emergent property of the universe's thermodynamic properties, heavily influenced by entropy. In his view, time isn't a fundamental aspect of reality, but rather a consequence of how we perceive the flow of information and the increasing entropy of the universe.
So you're saying that time might be an illusion, a product of our limited perspective within a universe governed by entropy.
It's a possibility.
My brain is officially hurting, but in a good way, I need a moment to process all of this.
It's a lot to take in, and this is really just scratching the surface of what these brilliant minds are exploring.
Right.
But it highlights how entropy is not merely a scientific concept, but a profound philosophical question that touches on the very nature of reality time and our place in the cosmos.
Absolutely. And speaking of our place in the cosmos, we've talked about the big picture stuff.
Yeah.
The fate that the universe black hole is the arrow of time.
Right.
But what about the impact of entropy on a more human scale? What about its role in society, culture, and even our everyday lives?
That's a great point. You know, we can see entropy's fingerprints all over human history and culture.
Okay.
Think about the rise and fall of civilizations.
Right.
Empires expand resources, are depleted, social structures become rigid, and eventually things fall apart. It's almost like a societal version of entropy, where order gradually gives way to disorder.
So the Roman Empire, the collapse of the Mayan civilization, these could be viewed through the lens of entropy.
Exactly. And we can see it on a smaller scale as well. Think about economic systems.
Right.
They're constantly struggling to maintain order and stability, but entropy is always lurking, threatening to disrupt markets and create chaos. Or consider environmental degradation. As we consume resources and pollute the planet, we're essentially increasing entropy, pushing ecosystems towards disorder and collapse.
It's almost like entropy is a reminder that nothing lasts forever, that change is inevitable, and that even the most complex systems are vulnerable to decay and breakdown.
Mm-hmm.
It's a bit sobering, but also kind of liberating in a way.
I agree, and it connects to how entropy influences artistic expression.
Right.
We talked about Andy Goldsworthy's ephemeral sculptures and the Romantic era's fascination with ruins. These works capture the beauty and melancholy of impermanence, the idea that entropy is not just a destructive force, but also a creative one.
And what about music? We talked about Ligeti and his influence on film scores, but are there other examples of entropy in music?
Definitely think about genres like punk rock with its raw energy and rejection of structure, or experimental electronic music that embraces randomness and noise. These forms of musical expression can be seen as embracing the entropic aspects of sound and pushing the boundaries of what we consider musical.
So entropy isn't just about disorder.
Right.
It's about transformation, evolution, and the constant interplay between order and chaos.
Precisely. It's a fundamental principle that reminds us that the universe is a dynamic and ever-changing place. And as we continue to explore entropy's implications, we're bound to uncover even more profound insights into the nature of reality and our place within it.
Well, I think we've all had our minds thoroughly expanded today.
I think so.
It's amazing how exploring a seemingly simple concept like entropy can lead us down these incredible rabbit holes of scientific discovery, philosophical inquiry, and even artistic inspiration.
It's a testament to the interconnectedness of knowledge and the power of curiosity.
Absolutely. For our listeners who are now eager to dive deeper into the world of entropy, we highly recommend checking out the work of the researchers we mentioned, Sean Carroll, Lisa Randall, Carlo Ravelli.
Yeah, they're great.
They're incredible guides to this fascinating, complex topic.
And don't forget to look for examples of entropy in your own life.
Oh, yeah.
It's all around us, from the way your coffee cools down to the way information spreads online.
That's a great reminder. Entropy is more than just a scientific concept. It's a lens through which we can view the world and understand the forces that shape our lives. So keep exploring with curiosity and an open mind. Until next time, keep diving deep.